So subatomic particles are the particles inside of an atom. Subatomic means smaller than atoms. So the three subatomic particles that you need to know about are protons, neutrons, and electrons. There are other particles in there, but at this level of chemistry, we don't care about them. So protons and neutrons are nearly identical in mass, and for our purposes, we can think of them as being the same. So the mass of a proton and the mass of a neutron, you can see it differs in the fourth significant figure here. They're both about 10 to the minus 27 kilograms. The mass of an electron is significantly smaller, almost 2,000 times smaller. And so the relative sizes of these particles, the protons and neutrons would be like a baseball, and the electrons would be like a grain of rice. Much, much smaller. So kilograms or even grams or micrograms or attograms are not good units for measuring the mass of these tiny, tiny particles. So they made up a different unit called the atomic mass unit for measuring the mass of an atom. Atomic mass unit. It's got a strange definition. One atomic mass unit, one AMU, is defined as 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. So most carbon atoms have 6 protons and 6 neutrons. And carbon is very stable, it's very common and easy to get a hold of, and so they said, okay, that carbon atom weighs 12 atomic mass units, so 1/12 of that is 1 atomic mass unit. That makes the proton or the neutron approximately 1 atomic mass unit. And that's as precise as we need to go. Protons and neutrons, 1 atomic mass unit. The charge of the proton and the electron are equal in magnitude. They're equal in size, but opposite in sign. One's positive, one's negative. So if we have those two particles together, they're neutral. So if we have an equal number of protons and electrons in an atom, the atom will not have an overall charge. The neutron is neutral, it has no charge. So what do we need to know out of this table? Well, we need to know the names of these particles, protons, neutrons, and electrons. We need to know approximate masses. We don't need all those sig figs. Proton and neutron, approximately 1 atomic mass unit. Electron, approximately 0. And then their relative charges. Protons +1, neutron is neutral, electron is -1. These are their actual charges, and these are their masses in kilograms, but don't even try to memorize those. Okay? If you need to use them on homework or something, you can just look them up. I don't remember those. If I don't remember something, you shouldn't have to remember it. So matter is usually charge neutral because we've got equal numbers of protons and electrons. But sometimes we get a charge imbalance. Those imbalances are unstable and they will tend to equalize quickly and often dramatically. An example of this is lightning. So this is just the very skimpy explanation, but there's negative charge that builds up on the clouds and positive charge builds up on the ground. And lightning is when that charge difference is equalized. There's a lot of energy in that, and it's so violent it makes this huge thunderclap. Right? Static electric shocks are also a charge imbalance equalizing. Any questions? So the number of protons in the nucleus is what defines that atom as being a particular element. This is called the atomic number. The atomic number is the number of protons. It has the symbol Z. Historical reasons for that. I'm not going to try to mix you up about which one's A and which one's Z, because I think A should be atomic number. Because they say A, right? Why should atomic number be Z and the mass number is A, right? So I'm not going to try to mix you up about that, but the atomic number is the number of protons. So if we look at helium, every single helium atom has 2 protons in its nucleus. That's what makes it helium. So this is like the personality or the personhood of the atom. So that's who you are. You can change what you look like. You could dress up like a gorilla. You could put crazy clothes on and make yourself look different, right? Those are kind of like the electrons. But the number of protons is who you are. You can't change that. All carbon atoms have 6 protons in their nucleus. So on the periodic table is a lot of hidden information. That's like the ultimate cheat sheet for chemistry. So let's look at this one on the screen. So here we have the chemical symbol is in the middle. We'll talk about those in a second. And above it, we have a whole number. That is the atomic number, the number of protons. And so all these different elements, they all have a different number of protons. And there aren't any that are missing, right? We've got 1 through 118 on here. And they have found or created an element with each of these numbers of protons. So, how many protons does a nickel atom have? Well, we find nickel, and it's the number above 28 protons. That's the atomic number. So we have a unique atomic number for each element and also a unique chemical symbol that's really an abbreviation of its name. Chemical symbols, which are on your memorization list, and remember, you should take that memorization quiz. It's due by Thursday at midnight. Elements have names, and they have symbols. So helium is its name, and so its nickname or symbol is capital H, lowercase e. The first H is always capitalized, the first letter. If there's a second letter, it's never capitalized. Always, always. The symbol for carbon is C. So those kind of make sense, right? He is the first 2 letters of helium. Helium can't be H because hydrogen is H. So it needs a second letter to distinguish it. So most of those chemical symbols are based on English element names, but some are based on Latin or even Greek names. So Na is the symbol for sodium. In the word sodium, there's no N, there's no A. It doesn't make any sense. Unless you realize that it was originally called natrium, and it is in fact the first 2 letters of its original name. So some elements have different names in different languages, but we all use the same chemical symbols.
Like silver is A something?
Silver is Ag because its Latin name is argentum. And some of them are pretty weird. Plumum, wolfram. Tungsten is wolfram. That's why it's a W. Yeah, it was really kind of crazy. So a slight variation from Dalton's law is that atoms, or his theory, atoms of a given element all have the same number of protons, but they can have different numbers of neutrons. So all atoms of an element are the same in the sense that they all have the same number of protons, but you can have different varieties of, say, carbon atoms, and they have different numbers of neutrons. So those are called isotopes. Atoms that have the same number of protons, but different numbers of neutrons. So as an example, looking at neon. So neon is number 10 on the periodic table. All neon atoms have 10 protons. But some have 10 neutrons, some have 11 neutrons, and some have 12 neutrons. Why? Because we found neon atoms, and that's what we found. There's no real good reason why it's those. But there are 3 different neon isotopes that exist, and because they have different numbers of neutrons, they have slightly different masses. Now, you might think they were like evenly distributed. Well, there's 3 of them, so a third of them are 10, and a third of them are 11, and a third of them are 12. No. They just are what they are because some of them are more stable than others. And so they just need to take samples and measure the abundance, the percentages of each of the different isotopes. And so those are called natural abundance, usually expressed as a percentage. No matter where you get that element from, the natural abundance of isotopes is going to be remarkably similar. Not exactly the same, but remarkably similar. So the mass number, which has that symbol A, is the number of protons plus the number of neutrons. So these are the particles that have mass, approximately 1 atomic mass unit, right? So if you take the number of protons and the number of neutrons in the nucleus, that gives you the mass number, gives you the approximate mass of the isotope. We can symbolize isotopes in a couple of different ways. This is often referred to as a nuclear symbol, where the capital X would be the element symbol. So down here we have 3 different isotopes. I should probably space them out. They don't need to be so close together. This is before COVID. So here's the X, the chemical symbol, right? And then to the left, there's a superscript. That's the mass number, and the atomic number is on the bottom. So I used to have a hard time remembering which one goes on the top and which one goes on the bottom. So this is what made sense to me. If you take the mass number and subtract the number of protons, you get the number of neutrons. So it's like sitting there ready for you to do the subtraction. The mass number is protons plus neutrons. The atomic number is just the protons. If you subtract, you get the number of neutrons. So we can represent these elements with symbols like this. We can also represent them using their chemical symbol followed by their mass number, or their element name followed by the mass number. Because really, if we know that it's neon, do we have to have the atomic number written on there somewhere? No, we don't, because we have a periodic table. You can't do chemistry without access to a periodic table, right? So if you need to know how many protons neon has, you just look at the periodic table and you're like, oh, 10. That doesn't have to be part of the symbol. So this would be like neon 20, neon 21. And so this is just summarizing these 3 different isotopes, a couple of different ways to indicate what they are. They all have 10 protons. Number of neutrons is different. So the mass number is 10 plus 10 is 20. 10 plus 11 is 21. The natural abundance, that is something that has been experimentally determined. And for neon, a little over 90% of the atoms are neon 20. Less than 1% are neon 21, and only about 9% are neon 22. Just because that's how it is. Any questions? So you should be able to answer questions like this. What are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? And you'd need a periodic table to do this. I don't care if you remember which atomic number or mass number is A or Z. I don't care about that. The mass number reflects the mass of the nucleus. So that's the total neutrons plus protons. The atomic number is just the number of protons. So for carbon, how many protons does carbon have? 6. We'll just find it on the periodic table here, and it has 6. That says 6 protons. So instead of writing out atomic number, I'm going to use its symbol Z. So Z equals 6. There's 6 protons. What's the mass number for this particular isotope? 13. We have to take the number of protons and add the 7 neutrons. So the mass number is 13. And then the symbol. So the nuclear symbol would be carbon, and we put the mass number on top and the atomic number on the bottom. Or we could also call this C13. If you're given a symbol like this, you should be able to identify how many protons, how many neutrons, even how many electrons. So how many protons does krypton 39 have? 19. We don't need to look at the periodic table even, because this is the number right down here. But if we find it on the periodic table, it is indeed number 19. So it has 19 protons. How many neutrons? 20, because we're going to take that 39 minus 19, 20 neutrons. How many electrons does it have? 19, the same as the protons. So I mentioned that electrons are, kind of on the outside, and you can actually gain electrons or lose electrons. But when this happens now, it's no longer an atom, it becomes an ion. An ion is an atom with a charge on it, be positive or negative. And this can happen during chemical changes, chemical reactions. So sodium can lose an electron and become a positively charged ion. Sodium originally had 11 electrons and 11 protons. If it loses an electron, now it only has 10 electrons, 10 negative charges, 11 positive charges. So we show the charge of the ion as a superscript to the right. If it's a 1, we don't write 1s. We'll leave 1s out a lot. But here we do write the sign, and that's different than math exponents. In math exponents, you only write the sign if it's negative. You wouldn't write the sign if it's positive. So one of the ways I rationalize this to myself is like, well, oxygen has a 2- charge. If we wrote it as O minus 2, that can get confused with a capital O variable raised to the -2 power, right? But this looks wrong for an exponent because it is wrong. This is how we indicate charges. So we put the number first and then the charge, whether it's positive or negative. Calcium has a 2+ charge, and so we don't just write 2, we write 2+. Here, fluorine can gain an electron and become a -1 charged ion. These ions have names. Cations are positive. Cations are positive, and anions are negative. Somebody last night pointed out that you can also think of the T in there as being like a plus sign. They both end in ion, but this one has an extra N. This is the -1. We need to keep those straight. Cations are positive, anions are negative.